Picture this. You just laid down a visually perfect, like totally Instagram-worthy weld. Flawless, even ripples. You lift your helmet expecting a clear pass, but the assessor just looks at the metal, then looks at you and slaps you with a not yet competent rating. You failed.
Yeah, that happens a lot more than you'd think.
Welcome to the deep dive. We're taking the official Comprehensive Assessment and Review Guide for the Shielded Metal Arc Welding National Certificate Level 2, or SMAW NC2, and we are unpacking the brutal hidden realities of what it actually takes to pass.
Right.
And for you, the listener, whether you are a student preparing for this specific assessment or just someone fascinated by, the extreme physics of melting metal, take a breath. This isn't a rushed cram session.
No.
We're keeping a steady, regular conversation pacing today, really digging into the invisible science behind the certificate. Because, like you said, a shiny bead on a piece of steel is incredibly deceiving.
Oh, absolutely deceiving. Assessors are looking way past the final product. I mean, they are grading the invisible metallurgy, the strict safety procedures, your setup, your underlying technique.
Yeah.
Producing a beautiful weld unsafely or without the right reparation, it doesn't prove you are a competent welder. It just proves that, well, on this specific day, you got lucky.
And nobody hands out industrial certifications for luck.
Exactly.
So I want to look at how a student even gets to the point of striking an arc, because the assessment starts the exact second you walk into the room.
The very second.
Right. If your attitude grooming and your personal protective equipment, your PPE, aren't flawless, you are out. We're talking welding helmet, welding gloves, leather apron, safety shoes, long-sleeve protective clothing, safety glasses. I mean, I used to think the heavy leather gear was just to stop a stray spark.
Yeah.
But looking at the actual hazards, it reminds me of an astronaut spacesuit.
That's actually a really good way to put it.
Like, if an astronaut skips one small step or ignores a tiny tear, the vacuum of space gets them. And here, you are essentially creating an extreme localized environment right in front of your chest.
Yeah, it's a micro-environment of extreme violence. I mean, every time you turn that machine on, you invite the big four hazards right into your workspace.
Which are?
Electrical shock from damaged cables, severe fire hazards, toxic fumes that can permanently damage your respiratory system, and intense radiation.
Okay, the radiation is what really caught me off guard. You think of welding and you think of heat. You don't necessarily think of UV rays.
Right, but the plasma arc gives off massive amounts of ultraviolet and infrared radiation. I mean, if any bare skin is exposed, you get severe skin burns in minutes, like a terrible sunburn.
Wow.
But more dangerously, if that UV light hits your unprotected eyes, it causes something called arc eye.
Arc eye.
Yeah, the radiation literally burns the cornea of your eye. It feels like someone poured hot sand under your eyelids.
Oh man, that sounds agonizing, which completely explains the incredible strictness around the always and never rules. Like you never weld near flammables, you never use a cracked electrode holder, and there's a specific check for the auto-darkening helmet. You have to test the filter before you even strike the arc. I always assumed you could just pull the helmet down and, trust it.
Oh no. Trusting untested safety gear in a shop environment, that is a massive behavioral red flag for an assessor.
Really?
Yeah, if you pull down a helmet with a dead battery and that filter doesn't darken the exact microsecond the arc strikes, you get a huge dose of that radiation.
Right.
And taking a shortcut, like using a cracked electrode holder just because you're in a hurry, automatic failure.
Because of the electrical shock risk.
Exactly. An assessor sees cracked insulation, and they see a lethal electrical path right into your hand. They are grading how you will behave in a busy shop when no one is watching.
So you've survived the setup, your spacesuit is pristine, and you haven't been failed for a cracked piece of plastic. But your PPE only protects your human body. What protects the actual molten metal from the chaotic air around it?
Well, that comes down to the equipment.
Right, and I want to understand the secret language here, because I always assumed welding just meant like plugging a machine into a wall. But the guide talks about alternating current versus direct current, AC and DC. Does the direction of the electricity actually change how the metal melts?
It dictates the entire behavior of the plasma arc.
Really?
Yeah. So direct current, or DC, flows continuously in one direction. That steady stream provides a very stable, smooth arc, which gives the welder precise control over how deep the heat penetrates the metal.
Okay, so what about AC?
Alternating current, AC, flips its direction back and forth many times a second. AC is typically used to solve a specific problem called arc blow.
Arc blow.
Right. When you weld with DC, a magnetic field can build up in the steel plate and literally blow or pull your plasma arc off course.
Wow, like a magnet deflecting a stream of water.
Exactly like that. AC's firing current breaks up that magnetic field so you can keep welding straight. But for pure control, DC is the absolute standard.
And you need that control because of the specific electrodes you have to master. We've got the E6E11, which the guide says provides deep penetration to blast through dirty or rusty metal.
Yeah, very aggressive rod.
Then we've got the E6E13, which produces a smooth, easily controlled arc, good for beginners. But the absolute king of this assessment seems to be the E7018.
Yeah.
The guide spends a massive amount of time on this specific rod.
Oh, yeah. The E7018 is a low-hydrogen, high-strength electrode, and it is basically the backbone of structural welding. Assessors will drill you on how to decode that name.
Okay, so break it down for us.
So the 70 stands for 70,000 PSI minimum tensile strength.
Let me stop you there, because 70,000 PSI is just a big number on a page. Yeah. To put that into perspective for you listening, imagine hanging 3 full-size elephants from a single square-inch rod of this metal, and it wouldn't snap.
Wow.
It is astonishingly strong.
Yeah, it is true structural-grade material. Then the one in the name tells the welder the rod can be used in all physical positions.
Meaning?
Flat on a table, horizontally on a wall, vertically upwards, or even fighting gravity overhead.
Nice.
And finally, the 8 describes the specific chemical makeup of the coating on the outside of the rod.
Oh, here is where I have to push back a little, because the physical handling of these E7018 rods seems almost paranoid. The requirements state they must be kept in a heated rod oven, sometimes at hundreds of degrees, right up until you use them.
That's right.
I get the safety gear, but failing a student just because their electrode was left out on a table, it's literally a metal stick. How much damage can a humid room actually do to solid steel?
Well, the vulnerability isn't the solid steel core, it's that flux coating baked onto the outside. That dry, chalky crust is the secret to the entire SMAW process.
How so?
As the steel core melts, that flex coating burns off and creates a dense, shielding gas. That gas pushes away the oxygen and nitrogen in the ambient air, which prevents them from contaminating the molten metal puddle.
Okay, so the crust makes a gas shield to protect the puddle. But why does it need an oven?
Because the chemical makeup of the E7018 flux is highly hygroscopic.
Meaning it pulls in water.
Exactly. It acts like a sponge, actively pulling humidity straight out of the air. If you leave it on a table, it absorbs water. Now think about what happens when you strike an arc that burns at several thousand degrees, and that heat hits trapped moisture in the flux.
It instantly vaporizes. It turns into steam, right?
More than steam, actually. The extreme thermal shock literally splits the H2O molecules apart into hydrogen and oxygen gas.
Oh, wow.
And the hydrogen gets trapped inside the liquid metal of your weld. As the weld cools and hardens into solid steel, those tiny hydrogen atoms are stuck inside the crystalline structure.
That sounds bad.
It is. They look for ways to escape, creating immense internal pressure that tears the metal apart on a microscopic level. It's called hydrogen-induced cracking.
That is terrifying. Yeah. So you lay down a weld, it looks flawless to the naked eye, the ripples are beautiful, but internally, just because the room is a little humid, the metal is full of microscopic fractures waiting to fail under load.
Which is exactly why using a cold, wet, or chipped electrode is an instant preparation fault. The science doesn't care how steady your hand is. If there is moisture in that flux, the structural integrity is compromised, period.
That invisible chemistry directly dictating physical strength is just wild to me. And it leads to a fascinating realization from the guide. When a welded joint does fail under stress, the crack usually doesn't happen in the melted weld bead itself. The failure happens just outside the weld in what is called the heat-affected zone, the HAZ.
Yes. Every single time you strike an arc, you create 3 distinct zones across the metal. You have the weld metal, that's the center pool that turned liquid and mixed with your filler rod.
Okay.
On the far edges, you have the base metal, the steel that stayed cool enough that its properties didn't change at all. And sandwiched right between them is the heat-affected zone.
It makes me think of a toasted cheese sandwich.
Okay, I like where this is going.
So the cheese in the absolute middle melts into a completely liquid state that's your weld metal. The bread crust on the very far edges stays soft and unchanged. That's the base metal. But the bread right next to the cheese, it didn't melt, but the extreme heat completely transformed its texture. It dried out. It became hard and much more brittle than it was before.
That is a perfect analogy. The metallurgy works exactly the same way. The extreme heat gradient from the arc alters the microscopic grain structure of the steel in the HAZ without ever actually melting it.
Wow.
It becomes incredibly hard, but also very, very brittle. It is almost always the weakest link in the finished joint. Assessors will hammer students on this concept during the oral examination, because if you don't understand the brittle nature of the HAZ, you won't understand why controlling your cooling rate is a matter of life and death.
Ah, that explains the heavy insulating blankets mentioned in the procedures. I always assumed you'd want hot metal to cool down quickly so you could unclamp it and move to the next piece.
Oh no. Quenching, or rapid cooling, is the absolute enemy of high-strength steel. A rapid drop in temperature shocks that altered grain structure and locks in severe internal stresses.
It freezes the stress in place.
Exactly. It also traps any of that stray hydrogen we just talked about. By using preheating techniques or wrapping the finished weld in insulating blankets, you force the metal to cool down incredibly slowly.
What does that do?
This gives the hydrogen time to diffuse out of the metal naturally, and it allows the crystalline structure to relax, which relieves those internal stresses.
The physics underneath all this are staggering. And this heat management ties right back into how you set up your machine, specifically your polarity. You mentioned earlier that direct current lets the welder control the polarity. There's DCE, which is direct current electropositive, or DCEN, direct current electronegative. Why does the direction of the electricity change how the metal melts?
It changes where the majority of the thermal energy is focused. So in an electrical circuit, electrons flow from the negative pole to the positive pole. If you set your machine to DCEP electrode positive, the electrons blast out of the steel workpiece and slam into your electrode rod. Because of the physics of the plasma arc, the positive side of the circuit takes about 2/3 of the heat.
Okay.
So in DCEP, the intense heat is driving deep into the metal, giving you maximum penetration.
So if I'm welding two thick, heavy plates of steel for a bridge, I want DCP. I need that heat digging deep into the root of the joint.
Exactly. But what if you need to weld thin sheet metal? If you hit thin metal with DCEP, you will instantly blow a molten hole right through it.
Because it's too aggressive.
Right. So you switch to DCEA electrode negative. Now the workpiece is positive, the heat profile completely changes, and you get a much shallower, wider melt pool that won't destroy thin materials.
And there's a brilliant troubleshooting insight here. If a student is in the booth trying to weld two thick plates together and they notice their puddle isn't penetrating deep enough, their first instinct is going to be, I need more heat, let me crank up the amperage.
That is a very dangerous instinct. If you crank up the amperage to compensate, you just create a massive, unstable puddle that throws sparks everywhere and probably undercuts the metal. A competent welder stops and checks their polarity first.
Oh, interesting.
Poor penetration is very often a polarity problem. You don't necessarily need more heat. You just have the heat focused in the wrong direction.
So your machine is set, your chemistry is controlled, your polarity is locked in. Now the physical act begins. Once the arc strikes, the manual shifts focus to the art of execution. An assessor requires you to look at a finished weld bead and read it like a forensic detective at a crime scene.
That's very true. When an assessor looks at your steel plate, they aren't looking for art. They are reading the physical evidence of your fluid dynamics. Once the arc is struck, 4 variables dictate everything.
Which are?
Amperage, arc length, travel speed, and electrode angle.
Let's look at the fluid dynamics of a bad bead. Say you lay down a weld that is incredibly narrow, looks like a piece of rope sitting on top of the plate, and has a high peaked crown.
Well, the physical evidence says your travel speed was far too fast. You rushed it. You didn't allow the arc to dwell on the joint long enough to properly melt the surrounding base metal.
So it's just sitting on top.
Exactly. The filler metal just piled up on top without fusing to the root. It's structurally hollow.
What about the opposite? The bead is incredibly wide, completely flat, and looks like a messy spill.
Your travel speed was too slow. When you move too slowly, the intense heat has nowhere to go but outwards into the plate. You are effectively digging a wider and wider crater and dumping excess filler metal into it. It flattens out like spilled soup. And worst of all, it usually causes a major defect called undercut.
Right. Undercut is when the arc literally melts a physical groove into the base metal right along the edge of the weld, but fails to fill it back in with new metal. It creates a stress point.
Exactly.
Then you have porosity, which are those trapped gas bubbles from bad flux or wind blowing away your shield gas. You have excess spatter. And you have slag inclusion, where the brittle flux crust gets trapped under the liquid puddle and hardens inside the joint.
And almost all of these visible defects trace back to those 4 root causes. Wrong amperage, poor travel speed, bad angle, or a fluctuating arc length.
For example.
If you see BB-sized spatter fused all over your plate, your arc length was too long. The plasma stream was erratic and violently throwing liquid metal out of the puddle. If your bead is uneven and lumpy, your arc length was too short, and the rod kept physically jamming into the puddle.
So let's say I'm taking the practical test. I strike the arc, I start dragging the puddle, and 2 inches in, I realize my angle is wrong. The puddle is getting ropey and lumpy. I know I messed up. Can I just quickly correct my hand angle, finish the rest of the plate perfectly, and then quietly go back with an angle grinder and smooth out those first 2 inches so the assessor doesn't see it?
That exact instinct is what separates an amateur from a professional, and it will get you failed immediately.
But why, if the final product is fixed?
Because a bad start doesn't just spontaneously self-correct. If those first 2 inches are lumpy, a fundamental parameter is broken. Assessors are listening to the sound of your arc.
The sound?
Yes. A perfect arc sounds exactly like crisp bacon frying in a pan. If it sounds like a hollow, erratic crackle where you feel the rod sticking, covering it up is a massive failure of integrity.
So what is the actual protocol?
You break the arc. You stop welding. You grab your grinder and you completely excavate the defective section down to shiny metal.
Start fresh.
Exactly. Then you step back, diagnose the root cause. Was my ground clamp loose? Was my amperage too cold? You fix the problem, and then you strike the arc again. Hiding a defect under a smooth grind job might pass a visual inspection, but it will snap in half the moment it is put under real-world stress.
That emphasis on diagnosis brings us to the final hurdle, the mental game. Passing SMAW NC2 requires navigating bureaucratic testing language like task management versus contingency management.
Yeah.
I want to translate that jargon into the real-world shop realities the S's are actually looking for.
Well, the assessors aren't just looking for a human robot who can weld perfectly when the weather is nice and the equipment is brand new. Task skills prove you can physically melt the metal, but contingency management is just a fancy way of asking. Do you freeze up in panic when your machine unexpectedly dies, or do you have the presence of mind to logically troubleshoot?
Let's run through some of these contingencies. You're in the booth, the clock is ticking down on your assessment, you lower your helmet, strike the steel, and nothing happens. The machine is completely dead.
Panic tells you the welding machine is broken and you're going to fail the exam. Contingency management tells you to trace the electrical circuit. 90% of broken machine issues are just a dirty or loose ground clamp on the table. You check the simplest, most logical connection before you assume a catastrophic failure.
What if you're halfway through a bead and you start smelling something sweet or acrid and you feel slightly lightheaded?
You drop your tools immediately, you leave the booth, get to fresh air, and notify the assessor.
You don't finish the bead.
Absolutely not. In the oral exam, assessors want to hear that you will aggressively prioritize your own respiratory health over finishing a piece of test metal. Deciding to just push through it because you were on a deadline is an instant failure in environmental safety.
There is also a huge emphasis on basic shop math and utilizing precise measuring tools, like a vernier caliper. They give a scenario where you finish your weld, it looks like a textbook example of perfection, but when you put the caliper on it, the bead is undersized by a single millimeter compared to the engineering drawing.
And that millimeter is the difference between a pass and a fail.
Seriously, just 1 millimeter.
In structural welding, a visual beauty never overrides mathematical load requirements. A weld that is undersized by 1 millimeter cannot physically hold the tons of pressure it was engineered to hold. An assessor wants to see you take out the caliper, measure the joint, acknowledge it is out of tolerance, and apply another pass of filler metal to bring it up to spec.
It's all about diagnosing reality over appearance. And during the terrifying oral drill at the end of the assessment, there's a specific way you are supposed to answer a question when you genuinely do not know the answer.
Right. If they ask you an obscure metallurgical question and your mind goes blank, do not try to bluff your way through it with a confident guess.
Bad idea.
A confident guess in a fabrication shop gets people killed. You look the assessor in the eye and say, I do not know the specific parameter from memory, but I know exactly which technical manual or engineering specification I need to consult to find the correct answer. They are grading your judgment.
We have covered a massive amount of technical ground today. And if you are studying for this assessment, I hope pacing through this has shown you that mastering the SMLNCE Tactical goes so far beyond just melting a stick of metal.
It really does.
It demands uncompromising, astronaut-level safety. It requires manipulating the invisible electron flow of polarity, managing the brittle crystalline structure of the heat-affected zone, reading the fluid dynamics of a liquid puddle, and maintaining the total mental composure to troubleshoot root causes when everything goes wrong.
Once you understand why the flux absorbs moisture, why a rapid cooldown traps hydrogen, and why an erratic arc creates a ropey bead, you are no longer just memorizing steps to pass a test, you are actively manipulating physics.
And it completely shifts how you view the world. I want to leave you with a final thought to mull over. We just spent this entire deep dive realizing that a perfectly executed, incredibly simple-looking strip of welded metal is actually the visible evidence of intense thermal mastery, invisible chemical reactions, and strict electrical manipulation.
Yeah.
So as you go about your day-to-day, look around you. What other simple physical skills or incredibly mundane everyday objects we take completely for granted are hiding an entire textbook of intense, unforgiving physics just beneath the surface?
It definitely forces you to appreciate the hidden engineering holding our world together.
It absolutely does.
Yeah.
Keep asking questions, trust the science, and we'll see you on the next deep dive.